those, that it should be biased correctly. Okay. So in this case, 3/4 of the time, you come to the conclusion that Coke is different than Pepsi. It is different. The two graphs are different. Here and Coke. Okay. So that's Coke or Pepsi. And NP, the form of ID. Oh, and then we showed that, well, we didn't show, but we concluded that NP actually equals P space. And in fact, this significantly enhances the ability of the verifier to verify things. So the prover, of course, the provers can do things that are beyond P space. The prover, anything that's definable, the prover can define. But working together, the verifier's powers are enhanced all the way up to P space from random P, from BPP, taken all the way up to P space. PPP would be no prover to put the point when it comes to express gas. Taken all the way up to P space by being able to talk with the prover about things and discuss things. Give hints from the prover. NP is a form of IT, one way of looking at it, in which the prover sends the one message that is the witness. Remember, what it is of NP is that NP is a situation where you have a verifier. In this case, the verifier, you can cut off the verifier's supply of random coins. Okay, he's on like Gamblers Anonymous. No coins. No. Take his head. No coins. Okay. And the prover doesn't really care what's being said to it anyway, and doesn't engage in long conversations. It just sends the witness stream. Because I've had it in a long time, or like I have like incredible, calculating powers, and I've decided that W is what you need in order to show that X is in the language if it is. And basically, it sets this probability all the way to 1. So, by definition, this just has to be a strong probability that if it's in the language, it accepts with that one string it closes. With NP, for verify the NP, no matter what you give it, it never accepts because it's not in the language. NP has that other flip side of it. It can't be fooled into accepting something which is not in the language. So, if it's not in the language, the probability B accepts given W is 0. Okay, the proof is smart enough to help V show things which are true, but not clever enough to fool V into things which are not true. That's the property of V, the verifier idea. So it was of itself an interesting class because, first of all, graph non-isomorphism was like a question that people really weren't able to place graph non-isomorphism and also graph isomorphism. They were funny problems. So a little bit the fact that this sort of, and I guess they kind of figured out that this Coke and Pepsi game would work. It's like street knowledge. That's the way of doing it. So they formalized it up in order to sort of figure out how they can formalize this intuition about these games these knowledge games, these information games, when you're comparing things and interacting. And the fact that it sort of ended up being in P space, sort of identified as another very natural class was interesting, and the fact that it's sort of restricted to another important class was interesting. But additional games followed soon, which was called zero knowledge. Okay? Because the deal there is you go back to this image of it where the verifier is trying to be convinced of the prover. So the prover is like, he's pleading with the verifier. It's like, look at all this proof I have of it being true. And the verifier is, okay. The game was how little can the prover say to the verifier in terms of knowledge? How little can it import to the verifier? And get the verifier to accept the statement. And the question was, can you get all the way down to nothing? And the verifier and the prover say only enough so that the verifier accepts that the string is in the language, that the graphs are non-isomorphic. Okay? But the verifier has learned nothing more. That's all it's learned. It's not even, the verifier hasn't even learned how to convince someone else of this fact. It's convinced of it. But, you know, when challenged on this, like, well, weren't you here when the prover was talking? Yeah, I was, but, you know, it didn't mean anything to me. Well, it was clear to me. So can you get down to this situation where nothing is learned except the zero knowledge? So the zero knowledge protocols then became invented and are useful for various things, are very much useful. They use a lot in cryptography and that sort of stuff. Okay. Where for example, we had just done in the earlier class, there's a situation of proving your identity by representing a password. The problem with all these password protocols is you give up something. And you show them your driver's license, and they say, oh, let me take a Xerox copy of it, okay? And of course, you know, that's okay. People, you know, they don't mess with this stuff that much, but there's police, you know, and rules, laws, and stuff like that. But you could ask for purely technical solutions where people cannot, where you can authenticate yourself to the person, producing some sort of credential that you have not given up at all. You have not really transmitted those credentials. The person is convinced that they have verified those credentials, but they have not learned anything about you besides that you seem to be who you claim you are. The driver's license has been produced and witnessed, but at the same time it has not. Then you wouldn't have to worry about, and what laws we need to do, and, whatever, but it was a pretty technical solution. So it was used in that context. And so here's an example of the zero knowledge proof. So the deal here is we're going to do an IP protocol